Okay, so we've been talking about decimal digits of integers. Now what about fractions? Certainly there are lots of numbers that have digits past the decimal point. So let's see how to deal with those numbers. Okay, once again, what we want to do is find a way, an equation that will give us the digits in an automatic way. As I've mentioned before, if you look at a decimal fraction like square root of 2 is 1.4142135, you can tell that the 1/10th digit is 4 and so on just by looking at it. But we want an equation that we could use a computer to find these digits. All right, so we're going to take off in a similar way as we did with integers. Remember with integers, let's scroll up here and you can see, we represented numbers with digits. D0 is the first one, then D1, D2, up to DM. Now let's go the other way. If we want to go the other way, well, 0 is the smallest positive number, so we want to go to D minus 1. D minus 1 would be the coefficient of 10 to the minus 1. All right, so we can continue the same pattern in a very reasonable way. So we're going to restrict ourselves to fractions that are between 0 and 1 because we've already taken care of the integer part. So we might as well just deal with the part that we haven't taken care of. Okay, so here we have this case. Now the difference between this case and the other case is that these can go on forever. Right? You know that numbers like pi and so on, they go on forever. Even some repeating fraction like 1/9 is 0.111111111 going on forever. So these digits may never end. Okay, so in order to compute these digits, we're going to use another function called the floor. So the floor function, I mean, you may have seen this before, is or you could also call it the greatest integer. So floor is the highest integer less than or equal to the given decimal number x, and is represented by the, this is what we call a floor symbol. It looks like a floor, so it kind of makes sense. Okay, so how are we going to use the floor function to find decimal decimal places? Well, let's do an example. All right, so let's go down here. This example of 0.17428. Okay, all right. So let's see. We want to find find its third decimal digit. Okay, so we're going to use two different methods like we did with the integers. First, we use recursive, and then we'll find the direct formula. First, let's use the recursive method. Find the digits one by one. Okay, we first notice the first decimal digit is the integer part of 10x. All right, so in other words, if I multiply this by 10, I'm going to get 1.7428. If I take the integer part, chop off the fractional part, I'll get the 1. Okay, so D minus 1, the 1/10th digit, is the floor of 10x. Okay, now if I subtract this from 10x, I'll get another fraction, and you notice that now the 1/10th digit was the 100th digit here. And we can do the same thing. All right, so just cutting to the chase down here, this is very similar to what we did with integers. We take our original number, we call it x now because it's not an integer, it's a real number, fractional number. All right, so what we do is we take 10 times our original number, take the floor, that's our 10th digit. Then we create this new number, b minus 1, which is 10x minus the 10th digit. And that means the 10th digit of the new number was the 100th digit of the original number. So we repeat the process. We multiply this new number by 10, take the floor, that's going to be our 100th digit. You subtract that off by taking 10b minus 1 minus d minus 2. Okay, so here's my process, iterative process, recursive process, just like we found recursive process for finding the digits of an integer number. All right. So this process can take a very long time if we're trying to find d minus k. All right, so is there an easy way to find individual decimal digits? Well, we can do something similar to what we did before. Instead of just multiplying by 10 and chopping and 10 and chopping and 10 and chopping, we can cut to the chase and go and multiply by some power of 10. If I'm looking for d minus 3, I can multiply by 10 cubed. Okay. All right, now if I do that, then I get this number 174.28. Now notice the ones digit here is exactly the digit I want, but I don't want the 17. Okay, but we know how to deal with that. We can get rid of the 0.28 by taking the floor, so that will take off the 0.28. We can get rid of the 1.7 by taking the remainder of this number mod 10. All right, so that gets mod d minus 3. So we can use that to get a formula, and the formula is here. What you do is you multiply to get the minus k digit. You multiply your original number by 10 to the k, take the floor, and then take the mod of the result by 10. So here you have some example to try some of these. All right. All right, now, since that was a short section, let's go right on to the next section. Of course, you've seen repeating decimals. Here's some examples, kind of interesting. Now, notice that this is 111, this is 0909. So this one repeats every 2 digits. This one repeats every 1, 2, 3, 4, 5, 6 digits. Now, what's the pattern here? Why does 1/7 repeat after every 6 digits and 1/11 repeats after every 2 digits? Doesn't seem to be a reasonable pattern here. I mean, so what's going on? How can we figure this out? Okay, so the question is, why do decimal fractions repeat? And what's the period when they do repeat? So you probably have never seen these answers to these questions before, when you've done lots with repeating decimals. So I think this should be an interesting section. All right, so first we're going to do some propositions, or actually we do just one proposition. All right, so let's take some integer n. So we want n to be bigger than 2, so that the GCD of n and 10 is 1. Okay, so this number n is relatively prime to 10. Okay, then there exists a positive integer m such that 10 to the mth, when I take the remainder of 10 to the mth mod n, I get 1. Okay, kind of interesting. If you think about that just on a cold basis, that seems, why should that be? But let's go ahead and do this. This is essentially a counting argument. Okay, we can take the remainder of 10, the remainder of 10 squared, the remainder of 10 cubed, and so on. Now, when I take remainders mod n, they're always between 0 and n minus 1. It will never be 0 because no power of 10 will have a common factor with n, because n and 10 are relatively prime. So if I raise 10 to any power, that power of 10 is still going to be relatively prime. Now, this is an infinite sequence, and it can only take at most n minus 1 values. So there must be 2 values that repeat. I don't know which 2 values there are. Let's say 10 to the k and 10 to the j. And we can choose them so that k is bigger than j. Okay, so we have so many values in this sequence, at least 2 of them must be the same because they're only n minus 1 distinct values. So I'm going to just choose 2 of them at random. Okay, now I can always also do this, mod 10 to the k. Now 10 to the k is just 10 to the j times 10 to the k minus j. That's your base, that's your exponent rules. Okay, but we know with modular arithmetic that we can break this up. The remainder of a product is the modular product of the remainders. All right, so if 10 to the k n equals mod 10 to the j n, I call this O dot. This is a multiplication in mod 10 with this number here. Okay, all right. All right, now look, we have this number, the remainder of 10 to the k equals the remainder of 10 to the j times this number. But we know the remainder of 10 to the k is the same as the remainder of 10 to the j. So I could just replace this one here with 10 to the j. So I have some number, some remainder, is equal to itself, O dot, this value. Now I know this value is in Z10. Now the only way that can happen is for this to be the identity in Z10. Okay, so this remainder must be equal to 1 when I take the remainder of 10 to the k minus j minus mod n. So, okay, so here we have a power of 10 whose remainder is 1 mod n. All right. All right. Now that's going to be very important because that's going to, in fact, this n is going to be the period of my repeating decimal. If I take 1 over n, the period of my repeating decimal is going to be this m. This m is in Mary. So that's how I do it. Let me just repeat what I said. If I take some number n, which is relatively prime to 10, and I want to find what's the period or the repeating period of 1 over n, I find a value of m, Mary, such that the remainder of 10 to the m mod n is equal to 1, and that m is the period. Okay, so we do this definition. So if I have a positive integer n, which is relatively prime to 10, the smallest positive integer m, such the remainder of 10 to the m mod n is equal to 1. This is called the multiplicative order of n. So Mary is the multiplicative order of Nancy. Right? So we can now prove that a lot of fractions repeat as follows. Okay. All right. No, so let n be some positive integer relatively prime to 10, and let m be the multiplicative order. Then the decimal expansion of 1 over n repeats every m digits. Okay. So what's the proof here? Given that m is the multiplicative order of n mod 10. So that means that we have 10 to the m, the remainder of 10 to the m is 1. Okay, so I can take 10 to the m minus 1, that's divisible by n, or I can write it this way. Okay, all right, so 10 to the n minus 1 over m, 10 to the n minus 1 over n is an integer. Okay, so I let k be this integer. Okay, so 1 over n is this integer k over 10 to the m minus 1. All right, let's do a little bit of factoring. We can factor out a 10 to the m out of the denominator, but then we have 1 minus 10 to the minus m left. Okay, here we can just do a geometric series now. This is going to be 1 and then some zeros and then a 1 and then some zeros and then a 1 and then some zeros and then a 1. Okay, so we factored this out, k over 10 to the m times blah, 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 blah. So we have k times 10 to the minus m plus k times 10 to the minus 2m. So, okay, so we just distribute this value. Okay, okay, now from the definition of k, we may conclude that k is less than 10 to the m. So you can think about why that is. It's not too hard to see if you look at the definition of k. Okay, all right, so k is limited in size. All right, so what does that mean? I will say that this is not written very well. What you conclude from this is that k has fewer than m digits. So what that basically means is that these different numbers don't overlap. From 10 to the minus 1 to 10 to the minus m, I have m different digits. So that k is going to fit in there quite nicely. From 10 to the minus m minus 1, 10 to the minus 2m, I still have m digits. That k is going to fit in there quite nicely. So this number and this number have distinct decimal fractions. Okay, and when I add them up, there's not going to be any carrying when I add this to this. All right, so that's why it says no two of the terms k times 10 to the minus m, k times 2 to the minus m, etc. have non-zero digits in the same decimal place. So this means that k is the repeating sequence in the repeating decimal, and there might be some zeros in front in case k is much smaller than 10 to the m. Okay, so k gives me my pattern. This k gives me my pattern, and m gives me my period of repetition. Now the proof we did for 1 over n turns out that we can extend it to any fraction j over n where the GCD of where n is relatively prime to 10. Okay, and in fact you can pretty much repeat the same argument to do this. All right, so I'm going to stop here and we'll have one more video on this chapter to talk about divisibility rules.